Ever pondered why clustering holds such a pivotal position in machine learning? It's a fascinating question, isn't it? Let's dive into it. Clustering plays a crucial role in machine learning, especially in unsupervised learning. It's a method of grouping data points with similar characteristics, which forms the basis for data segmentation, pattern recognition, and image analysis. Consider an e-commerce platform with millions of products. Clustering can help categorize these products into distinct groups based on their features, making it easier for users to find what they're looking for. Or think about a facial recognition system. Clustering aids in identifying patterns in the training data, allowing the system to recognize different individuals accurately. Moreover, clustering is the key to unveiling hidden structures in data. It's like a treasure hunt, where clustering algorithms search through vast amounts of data to discover valuable insights. Clustering, therefore, serves as a valuable tool in machine learning, aiding in the extraction of meaningful insights from vast data. Now, consider the K-means algorithm, one of the most widely used clustering techniques. The K-means algorithm is a beautiful dance of mathematics and data, and it all starts with the selection of K centroids. These centroids are initially chosen at random, scattered across your data like stars in the night sky. But these are no ordinary stars, they are the seeds from which our clusters will grow. Then the music begins to play and the dance truly starts. Each data point in your set takes a look around, and then, guided by the principle of distance, it waltzes its way towards the nearest centroid. In other words, every single data point is assigned to the closest centroid, creating a temporary cluster. But the dance doesn't end there. The centroids, those initial seeds of our clusters, then take a step. They recalculate their position, moving to the geometric mean of all the points currently assigned to them. Imagine a crowd of dancers swirling around a grand ballroom, and the centroid is the point in the middle, around which all the dancers revolve. This dance continues with the data points and centroids moving in response to each other. The data points reassign themselves to the nearest centroid, and then the centroids recalibrate their position based on their new followers. This two-step dance continues until there is no more movement. The dancers have found their partners, the data points have found their clusters, and the centroids have found their final positions. The beauty of the K-means algorithm lies in its simplicity and efficiency. It doesn't try to decipher the meaning of the data or make any assumptions about its structure. It simply organizes the data into K distinct clusters based on the principle of distance. So by iteratively adjusting the centroids and reassigning the data points, the K-means algorithm successfully creates K distinct clusters. This elegant dance of data and mathematics allows us to make sense of complex data sets, unveiling patterns and relationships that might otherwise remain hidden. And that, in essence, is the magic of the K-means algorithm. Despite its popularity, the K-means algorithm comes with its share of limitations. But before we discuss those, let's briefly recap the key points about K-means that make it such a widely used clustering algorithm in machine learning. Firstly, the K-means algorithm stands out for its simplicity. It's easy to understand and implement. You assign objects to the nearest cluster by distance, then compute the new mean or centroid of all objects in the cluster. Repeat these steps until the centroids no longer change. This iterative refinement procedure is what gives K-means its name. Secondly, it's efficient. The time complexity of the K-means algorithm is linear, which means it scales well with the size of your data set. So if you're dealing with a large data set, K-means is a solid option to consider. Thirdly, the algorithm is scalable. It can deal with high-dimensional data and is also compatible with most forms of distance measurements, including Euclidean and Manhattan distances. Now, despite these strengths, K-means is not without its drawbacks. One of the main limitations is its sensitivity to the initial selection of centroids. The final clustering result can vary significantly based on where you initially place the centroids. And while there are techniques to address this, there's no definitive solution. Another limitation is determining the optimal number of clusters, K. Too few clusters can oversimplify your data, while too many can overcomplicate it. Again, there are methods to estimate the best K, but they're not foolproof. Finally, K-means struggles with handling outliers and clusters of different sizes and densities. The presence of outliers can significantly distort the location of the centroid, leading to inaccurate clustering. Similarly, the algorithm assumes that all clusters have similar sizes and densities, which might not always be the case in real-world data. While the K-means algorithm has proven highly effective in many scenarios, its limitations necessitate the exploration of other clustering techniques for more complex data sets.